All right, it is it is 200. No, it is 2025, September 17th. September 17th, approximately 7:54 a.m. And today we are going to be continuing with Chapter 3, getting Chapter 3 problems out of the way here, starting with Chapter 3-1. Let P of n be equal to a sub d times n to the d plus a sub d minus 1 times n to the d minus 1 plus on and on and on until we get to a sub 1 times n plus a sub 0, with a sub d being greater than 0, be a degree d polynomial, in n, and let k be constant. Let k be a constant. Now, using the definitions of asymptotic notation, oh boy. Notations prove the following, which is, my goodness. Yeah, okay. A, if k is greater than or equal to d, then P of n is equal to big O of n to the k. B, if k is less than or equal to d, then P of n is equal to big omega of n to the k. C, if k equals d, then P of n is equal to theta of n to the k. D, if k is greater than d, then P of n is equal to little o of n to the k. E, if k is less than d, then P of n is equal to little omega of n to the k. So, intuitively, a degree d polynomial behaves like its leading term, a sub d, n to the d for large n. So it's bounded above by a constant multiple of n to the k when k is greater than or equal to d, bounded by below by a constant multiple of n to the k when k is less than or equal to d. Almost died. Goodness. Equal order when k is equal to d, vanishing relative to n to the k when k is greater than d, and dominating when n to the k, dominating n to the k when k is less than d. So how do we say that a bit more rigorously, right? Well, let's get into that. So, since a sub d is greater than 0, P of n is eventually is eventually positive, right? Let's fix A to be equal to that by saying A is equal to the summation from J is equal to 0 to D with the absolute value of A sub J. So for part A, let's say, okay, we have K is greater than or equal to D, and we want to show that that implies P of n is equal to big O of n to the K. And this is for all n greater than or equal to 1, right? So, so 0 is less than or equal to P of n, which is less than or equal to the summation from J is equal to 0 to D, A sub J, the absolute value of A sub J times n to the J, it's less than or equal to A times n to the D, which is less than or equal to A times n to the K. So, by definition, P of n is equal to big O of n to the K. Take C is equal to A and n naught to equal 1. Okay? Yeah, that fulfills this. Okay, now let's go on to B. Just sort of blanked out there for a moment. Okay. So for B, K is less than or equal to D, implies P of n is equal to big omega n to the K. Right, that's what we want to show. Let's split P of n to equal A sub D n to the D minus the summation from J is equal to 0. J is equal to 0 to D minus 1 of negative A sub J n to the J. What do we find here? Well, that's actually greater than or equal to A sub D n to the D minus the summation from J is equal to 0 to D minus 1 for absolute value A sub J times n to the J. This is for n is greater than or equal to 1. And what we have then is that this is, so the summation from J is equal to 0 to D minus 1 of the absolute value of A sub J times n to the J is in fact less than or equal to, open parentheses, the summation from J is equal to 0 to D minus 1 of the absolute value of, let me make those look like ones. So A sub J close parentheses times n to D minus 1. And that is in fact less than or equal to A times n to the D minus 1. Okay, so this is taking up a lot more board space than I anticipated, so just keep that in mind and we'll move on to the next part, which is to say, okay, let's choose n naught so large that A sub D to the n is greater than or equal to 2A for all n greater than or equal to n naught. E.g., that is, well, for example, I mean to say, no. No, n naught, there we go, is equal to ceiling function of 2A divided by A sub D. There's some construction going on, but then we can say for n is greater than or equal to n naught that P of n is greater than or equal to n sub D times n to the d minus big A times n to the d minus 1, which is, in fact, greater than or equal to a sub d over 2 times n to the d, which is, in fact, less than or equal to a sub d times, over 2 times n to the k. All right. Now, here's where things get a little more critical. We say, okay, let's see if I can fit this all over here, right? Let's see. Should be able to. Since k is less than or equal to d implies n to the d is greater than or equal to n to the k for n greater than or equal to 1. Right, so we can say then, so P of n is equal to big omega n to the k, right? There we go. QED. Let's move on to the next one, which is C. So for C, we want to show k is equal to d implies P of n is equal to theta of n to the k, right? So just checking. Okay, yep. Okay. So, well, what have we done with theta? What is theta basically, right? Well, from that, we combine, from what we've done before, we combine what we did in parts A and B with k is equal to d to obtain both big omega n to the d and big O of n to the d and big omega n to the d, right? So combining those two, we get this as a natural, not a natural result. I mean, human beings are natural, I guess. So it's like the ideas they concoct. Those are kind of natural, but suffice to say, this implies that that theta of so putting those two proofs together, right? Putting those two proofs from A and B together, we get that P of n is equal to theta of n to the k. So basically, let's put this a bit more formally, right? So those two proofs, right? So we had k is greater than or equal to d implies P of n is equal to big O of n to the k, right? That was A. Now, for B, we had k is less than or equal to d implies P of n is equal to big omega of n to the k, right? And so this implies that P of n is equal to theta of n to the k. And this works both ways. You could say, like, okay, by theorem, because we had that theorem earlier, where it's like, okay, if it's kind of like the squeeze theorem in a sense. It's kind of like sandwich theorem, I guess, in a way, intermediate value theorem, kind of. We looked at that earlier whenever we were looking at chapter 3 in the lecture, for the lecture for it, and we looked at this theorem, which said that, like, okay, if these two are the case, then we can say, yes, that is the case. But if you want to go a little bit further than stating this little line right here, then this is what you'd put. You could even argue just by strict definition, right? And you get the same thing. That pretty much holds for C for now. Let's move on to D. So for D, we have, we want to show that if K is greater than D, then P of n is equal to little o of n to the k. That's what we want to show. Now let's go and show that with some rigor and tact, right? So consider P of n over n to the k. And this is equal to the summation from j is equal to 0 to d of a sub j n to the j minus k. Now, since j minus k is less than or equal to d minus k, which is less than 0 for every j less than or equal to d, each term tends to 0 as n approaches infinity. By the way, I think it's kind of neat. Well, I don't know. I think it's kind of interesting that we as a species haven't exactly found like just a universally accepted way to say, to write 0 is different from O in any sort of significant way. There's like it's more narrow. It's more narrow. We could say that's 0 and this is O, right? No, but that's not like a big enough difference. Like, in terms of like saying things, right? Nah, but that is an interesting thing. It's irritating enough sometimes to be mentioned, but it's not irritating enough to develop a universal change in notation. So it's like the benefits of keeping it that way outweigh the costs of changing it. So, that's interesting. But anyhow, each term tends to 0 as n approaches infinity, right? So the sum tends to 0. By definition, P of n is equal to little o of n to the k, right? Okay. Yeah, I confused myself earlier back in the 3.3 exercises because I was like, isn't that supposed to be a strict thing? But it's not. Like, the definition itself isn't like, okay, this is supposed to be a strict thing. It's this part, that part's supposed to be strict, because if you look at it from the perspective of the definition, it's like you extrapolate from that to this. It's not like, okay, and you can turn it back and go the other way, right? But anyway, let's proceed to E. Finish off this problem before moving on to the next one. So for part E, we have to prove k is less than d implies P of n is equal to little omega is equal to, gosh dang it, man. Freaking bugs. Okay. Almost got him. Maybe I did get him. I don't know. Not usually optimistic on that sort of thing. Sometimes I really do get them. There's a mosquito flying around in here for whatever reason. It's like, oh, never mind. I can kind of see the reason. We're actually fairly close to the outdoors. Because I was like, we're on like the bottom floor of a massive building. Like, how on earth did a mosquito get here? It's like sometimes you're on a skyscraper and you see a wasp and you're like trying to get in, and it's like, well, we're on the 10th freaking floor. What is this thing doing here? It's like bugs are tenacious, man. But anyhow, k is less than d. That implies P of n is equal to little omega of n to the k. That's what we want to show. Again, we'll use this sort of what is it, squeezing. I mean, this isn't, I was almost going to say squeezing mechanism, but it's like, if you can get it to where it's like the difference here is greater than 0 or less than 0, then you can say quite a bit about it, something. So P of n over n to the k, which is equal to the summation from j is equal to 0 to d of a sub j times n to the j minus k, which is in fact equal to a sub d times n to the d minus k, plus the summation from d minus 1, from j is equal to 0 to d minus 1 of a sub j times n to the j minus k. So here, d minus k, that's greater than 0. So a sub d n to the d minus k that goes to infinity. So this goes to infinity, so a sub d times n to the d minus k goes to infinity. So this is while each remaining term is at most polynomial in n to the d minus 1 minus k, and cannot cancel the positive diverging leading term for large n. Therefore, p of n over n to the k goes to infinity. That is to say, p of n is equal to little omega of n to the k. Very good. On to the next one. Next problem, which is it's a bit lengthy, but I don't think it's too lengthy for what it is, for what that's worth. There are a few problems though. Okay, clear the board. So 3-2, which, you know, I forgot the title of the last one. The title of the last problem we did was asymptotic behavior of polynomials. This one's relative asymptotic growths, which is like, looking at this stuff is very valuable, not just for computer science, but also it's like, well, anything that we want to observe growing like ever. I mean, that's kind of an exaggeration, a hyperbole, but it's like, wow. It's like, look at like the way that cancer proliferates and stuff like that. And look at the way in which population distributions happen. It's like, well, looking at these things is a very valuable thing, just in general. So, but anyhow, we have indicate for each pair of expressions open parentheses a comma b, close parentheses, in the table, in the given table, whether a is 0, big O, little o, big omega, little omega, or theta of b. And we have here assume k is greater than or equal to 1, epsilon is greater than 0, c is greater than 1 are constants. And write the answer in the form of the table with yes or no in each box. So intuitively, we're comparing growth rates of common classes of functions. Right, so we have... Oh, I haven't even put down the table to really look at, but we'll look at it here in a bit. And basically, it's just... So all these different types of functions. Polynomials, polylogarithms, exponentials, factorials, variations of that. And the asymptotic hierarchy is like, well, you have like your constants down here. Well, let me, come on. Oh, come on. You gotta be kidding me. It's not kidding me. It is, in fact, not joking. One is vastly less than log of n, which itself is vastly less than log of n, which is vastly less than just vastly less than n to the c, which is vastly less than c to the n, which is vastly less than n factorial, which is vastly less than n to the n. So that's the hierarchy, which is a good thing to really remember, by the way. This thing, like that's pretty good. What is it like? I was about to say this one thing which I had remembered, which is like the encapsulation of all of these. Let me see if I can remember it. It's like these sets. It's like one of those things where it's like I kind of just take it for granted that I memorized it once, so I'm not really certain. Oh boy. Nope, no. That is not it. Okay. I think it's like the naturals are contained within the rationals. The rationals are contained within the integers, which are itself contained within the reals. So it's like that, in a way. This ordering, I mean to say, is very important. So yeah, it's like in terms of all of these functions here, the asymptotic hierarchy as well, constants are always going to be vastly less than log of n, which are going to be vastly less than log of n, which are going to be vastly less than n to the c for some constant c, which is going to be vastly less than some constant c taken to the power n, which is going to be vastly less than n factorial, which is going to be vastly less than n to the n. And so there's like nuances with growing variance, slowly growing variances, like log to the k of n, and open parentheses log of n, close parentheses factorial, and n to the 1 over log of n, right? So, and those are good to keep in mind. And whenever I show you the table, it's like you'll see like why, oh my goodness. Okay. So, how about this? I'll show you the table, because I don't want to write all that down, man. That's a lot to write down. And I mean, I know that's kind of funny because it's like, well, you write down a lot anyway, but I mean, like, this is a lot of just like, do I have to kind of thing, you know? Let me think about this. How would I show this? Okay, how about this? I'll just show you that, and then we'll work up to the table, okay? So that way there's no like trickery or anything like that, or, you know. So you see, this is the table we're working towards, and like picture it without these being filled out, right? So, yeah. So this is the table that we were supposed to do, which goes up to 30, by the way, which is absolutely freaking insane. But like, that's good. That's good to have that many things to discuss and look at for these cases, because it's important. But it's like, we'll see whenever I get to it, because we'll work up to that. And I'll probably get rid of this and exchange it for a new one here. So let's see here. Rigorously speaking, it's like, well, let's try and like, so the way that I approach this is like, let's take like these, let's break this thing into different sort of sets, different sorts of categories, different sorts of classes, whatever you have, groups, sorted. So let's sort these things into different types of things, right? So for instance, log to to the n, open parentheses, log of n, I mean to say, to the k. So open parentheses, log of n, close parentheses, to the k, which is equal to little o of n to the epsilon. And this is for any epsilon greater than 0. Polylogarithms. It's like, what are those going to be dominated by? Well, so let's just keep this here. So polylogarithms are dominated by polynomials. Right, that's a, yeah, so, and for n to the k, which is equal to, n to the k, that's equal to little o of c to the n. This is for any constant c greater than 1. Exponentials dominate polynomials. Now, okay, so this is like looking more closely at the hierarchy that I showed you there earlier. And c to the n equals little o of n factorial. This carries with it the same assumptions as we had earlier, so I'm not going to keep on putting that, but factorials dominate exponentials. There's like this one example here, like n factorial is greater than or equal to some open parentheses n divided by 2 close parentheses n divided by 2 to n divided by 2. Right. Now let's show the last of these generalizations before I go on to the board, to the actual table, I mean to say. So for n factorial, that's going to be equal to little o of n to the n. Each factor in n factorial is at most n. And this gives us that n factorial is in fact less than or equal to n to the n, right? Okay, now let's talk about this interesting case here, which we've looked at a bit, which is open parentheses log of n to the, well, the factorial of that. Well, that eventually grows faster than every polynomial n to the k, but slower than n to the epsilon. Got to be careful here, though, because I'm not going to put note, because these are notes. The whole thing is a note. Substituting m is equal to log of n What does that get you? Well, that gets you that log of n, I mean the open parentheses, log of n, close parentheses, factorial is equal to m factorial. Stirling's approximation. Shows m factorial is roughly equal to open parentheses m divided by e, close parentheses to the m. Since n is equal to 2m, 2 to the m. Since n is equal to 2 to the m, we compare, you know what, I'm just gonna, okay. Let's continue along this careful note here, this careful note of notes. Oh goodness, my eraser is just not doing it right now. There we go. Just a little more of the triceps to it, and it's like, break it. So, okay. Since n is equal to 2 to the m, we compare m factorial to n to the, which is equal to 2 to the, n to the epsilon, which is equal to 2 to the epsilon m. And as m approaches infinity, m log m eventually exceeds epsilon times m. So open parentheses log of n, close parentheses, factorial, that's vastly greater than n to the epsilon for any fixed epsilon greater than 0. So log of n, open parentheses log of n, close parentheses factorial outruns every polynomial. Okay, so we finished that careful look at log of the open parentheses log of n, close parentheses factorial. Now let's continue this thought process onto this last general instance, which I can point out for this table, which is this instance of n to the 1 divided by log of n. Now let's say this approaches 2. Yeah, this approaches 2, so n to the 1 over log of n is equal to theta of 1. So that's a constant. Now let's look at that table, right? Let's look at that table a bit more closely. Oh boy. Okay, there's like 30 of these. Should I... Okay. Do I write them down on the whiteboard? Do I break them out one by one? That would be nice, but do I have time for it? Do I have time for it? And is it... Okay. You know what? Why not? Why not? I'll do it. I'll break it down like a high school essay or like a rap at the rec center. Just okay. So remember, 1 vastly less than. Let's put this up here. 1 vastly less than log of n, which is vastly less than log of n, which is vastly less than n to the c, which is vastly less than c to the n, which is vastly less than n factorial, which is vastly less than n to the n. So keep that in mind. I don't know. Will I go through all 30? Let's see. How about this? Goodness gracious. Let's go through. You know what? I'll go through through 3 of them, which sort of show the general heart of the matter. Okay. Which are like the numbers 1, 15, and 30. So I'll just zoom in so you can see that. See the table right there in my notes. Again, this is a lot to type out. It's like, but it's like writing it on a whiteboard. It's kind of mechanical, and it just follows from the principles which we looked at. So for the first one, we have 1, A, B, big O, little o, omega. And instead of saying yes or no, I'll just put like a check mark, and I'll just put like a check mark or an X to denote the check mark for yes and the X for no. So let's look at this first one here, which is the log k to the n, and we have n to the epsilon. So how does that fit into our hierarchy? Well, let's look here. No discernible log k to the n sort of thing, but remember we had discussed that notion before of log k, log to the k of n. And what follows from that is like, yes, we do have the big O case. So remember that's, so the sentence is A is blank of B. So is it the case that the log to the kn is big O of n? Well, it's like it's little o of n, and little o is a stricter case, right? Yes. Can we say anything about the lower bounds? It's like, no, we cannot say that, and we cannot say that to be the case for theta either. Theta works 2 different ways there, so. Now let's go and look at 15 here. So, and if you want, just look at the notes, okay? Like, the notes should be available on GitHub by the time that you see this. So that way you're not missing too much by me not writing this out on the whiteboard, okay? So n to the log of n, that paired with this b here of open parentheses log of n, close parentheses to the log of n. So a, in this case, n to the log of n is what? Is what of b, which in this case is open parentheses log of n, close parentheses to the log of n. Can we say that it defines an upper bound in the way that big O does, right? Let's think about that. Let's think about our hierarchy, right? So it's like, yes, indeed we can. Yes. And we can define it strictly even. So, but can we look at the other things in that way? It's like, no, that's like vastly bigger. So no, no, no. Okay. Let's take a look at 30. N to the log C, C to the log N. This is a stranger one. So can we make any sense of like a strictness sort of thing? Well, it's like they're very, very close. These things are very, very close. And it's like, you know, we could discuss this more rigorously. In fact, like each of these could be, right? But just think about this sort of intuitively. These things are really, really close in terms of like, okay, they're using one of the slowest growing possible things, which is log of n, right? Or log of c. And they're taking that to be the exponent. It's like, so yes, we can define by what we have as like a loosely fitting, let's say, upper or lower bound. And that or is important because that says both. And because we're able to look at both of those things, can we say that like there's that this thing fits in between either of the two based on this other thing, right? Well, it's like, yeah, we can say that. But can we say without more concretization that that one is like strictly less than or strictly greater than, right? Well, it's like, no, we can't say that. We don't have the actual things to say that for certain. Because depending on what C and N are, right, C is going to be fixed, N is going to be growing. It's like, these things could be equal. These things could be equal. Well, okay, how do I say this? So it's like, I think like set C equal to 1, or like, okay, let me think a bit better on this. So depending on your base, right, you can set C equal to something, and it would be in such a way that these things, that you get very little to no change in either of these cases. So much so that you could say that there is a case in which these things are equal. I'm just like, I'm blanking right now, but you can sort of get where what I'm getting at, right, with this sort of like more tightly bounded versus loosely bounded sort of intuitionist approach on that. But each row follows from the hierarchy and identities listed at the top, plus Stirling's approximation for factorial related items. This fully resolves the yes or no classification of big O, little o, big omega, little omega, and theta for representative pairs spanning the problem's functional families. Now, filling the entire table, as I mentioned, is kind of mechanical. It's lengthy. Each entry follows from these hierarchy rules and standard tools like Stirling's formula, change of variables. For instance, like m is equal to log of m, limit definitions of little o, little omega, etc. The key, right, is, let me erase this. The key point here is recognizing the strict order of these classes. So log of n, log to the k of n to the 1 of log of n, that's going to be vastly less than n to the k, which is going to be vastly less than c to the n, which is going to be vastly less than n factorial, which, these two things, right, these two things here, like we saw in the last one, can be a bit confusing, but if you factor in the fact that we're using the logarithm in there, it's like, well, that sort of starts to make a bit more sense. But n factorial is vastly less than n to the n, and the table can be completed consistently with these asymptotic relationships, right? So, and that's a bit of what we looked at with those 3 instances on that table. And I might go back and do like all of the ones on that table, just as its own separate thing. Because I feel like that could definitely be valuable. Like looking more in depth at that table, just to sort of get a point across. But, for now, let's just stick to this is the takeaway, right? This is the takeaway. Let me add more to that. Let me add more to this, which is that, that other part, which I mentioned earlier. So it's like, okay, it's like all of this is true, but also it's like it's vastly, this is vastly, the constants are vastly less than log of n, right? So, what else can I say? I mean, I guess I should put here, right, that these are less than, oh, goodness gracious, vastly less than log of n. And that sort of completes the hierarchy, which is that, like, one is, the constant is less than, it's less than log of n, and log to the k of n to the 1 over log of n, which is vastly less than log of n, I mean to say, which is vastly less than n to the k, which is vastly less than c to the n, which is vastly less than n factorial, which is vastly less than n to the n. Okay? That's the sort of order we're looking at. Neat thing to remember. Comes in handy. All right, now let's take a look at problem 3-3, which is ordering by asymptotic growth rates. Okay. So we are told rank the given functions by order of growth. That is produce an arrangement G sub 1 all the way up to G sub 30, satisfying G sub 1 is equal to big omega of G sub 2, G sub 2 is equal to big omega G sub 3, so on and so forth until we reach the last one, which is G sub 29 is equal to big omega of G sub 30. And partition the list into equivalence classes so that f of n and g of n are in the same class. If and only if f of n is equal to theta of g of n, right? And for these, we're given 2 to the log n is equal to n, 4 to the log n is equal to n log of 4, which is equal to n squared. 2 log squared of n is equal to n log n, open parentheses log of n close parentheses to the log n is equal to n to the log of n. Log of n factorial is equal to theta of n log n. N to the 1 over log of n is equal to 2. That's what we're given. So let's sort of talk through this, right? So we'll get like strict cuts for this. So it's like, well, factorials versus exponentials, right? Stirling's approximation, we have open parentheses n plus 1 close parentheses factorial over e to the n approaches infinity, right? So we get this ordering right here, which is, you know, sort of functions, open parentheses, n plus 1 factorial, those are in fact, I'm going to use this symbol here, which is basically to say, is just finish that. Just from largest to smallest going here. Talking about factorials versus exponents. We're not really given n to the n in this case, right? This is the case of factorials versus exponentials. Now, how about exponentials? Well, super polynomials. Okay, so for exponentials, we have the case that like n 2 to the n divided by 2 to the n equals n, which approaches infinity, and e to the n divided by 2 to the n, that equals open parentheses e divided by 2 close parentheses to the n, which goes to infinity. And for super polynomials, which are below exponentials, 2 to the log squared of n and log of n, it's vastly greater than n to the log of n, which is equal to open parentheses log of n close parentheses to the log of n, which is vastly greater than open parentheses log of n close parentheses factorial, if we compare base 2 logs, right? So, and for polynomials, like in that case, it's like, well, n cubed is going to be, let's look at these sort of classes of these things, right? So, and it's by the ordering, which we had noted earlier. Also, 4 to the log of n is equal to n squared, and 2 to the log of n, that's equal to n. And between polylogarithms, we looked at that case, at least for the table, log of n factorial is equal to theta of n log n, which is vastly greater than log squared of n, which is vastly greater than the natural log of the natural log of n. Iterated log families. So the natural log of the natural log of n is vastly greater than 2 to the log, 2 to the log to the asterisk of n, which is vastly greater than log to the asterisk of log of n, which is equal to log to the asterisk of n, which is vastly greater than log of log to the asterisk of n, which is vastly greater than constant. And for a constant tail, but looking at like the tail of this, it's like, well, n to the 1 over log of n, it's like, well, we get 2, because remember, the base of this case, the base case. No, it's funny. But we'll get like an ordering of like some g sub I is equal to big omega of g sub I plus 1. We'll get that throughout. And functions in the same bracketed set are theta equivalent by the identities listed at the top. And I'll show that just now a bit more rigorously, right? Oh, okay. Such a way that we contain all of these different identities. Partition the equivalence classes. Okay, so we have the equivalence class of open parentheses n plus 1, close parentheses factorial. And this is from largest to smallest, right? So yeah, I'll just right here. Then there's the equivalence class of n factorials. Then there's like the n of it all. There's the n times 2 to the n. To the n, three halves to the n, two to the log square root of n, n to the log of n, open parentheses log of n, close parentheses to the log of n, n to the log of n, open parentheses log of n, close parentheses factorial, which of course, you know, those things are going to be greater than n cubed, which are going to be greater than 4 to the log of n squared, which is going to be, these things are going to be greater than log of n factorial n log n's, which are going to be greater than the 2 to the log of n's, and the n's, and these are going to be greater than the log squared of n's, which are going to be greater than the natural log of the natural log, which I should probably get into more. I should probably try to explain the difference between natural log and log a bit more, just in general, but for now, let's just keep it this way. We're talking about the equivalence classes, and so, which are, this case, it's like log to the asterisk of n, it's going to be less than that, and so let's go back here. Set, so the equivalence class log to the star of log of n, log to the asterisk. The iterative logarithm of n is going to be much greater than these are going to be much greater than the equivalence class of these individual sort of elements here. That's what I'm sort of getting at. I mean, I say equivalence class, I assume you know what that means, right? So, which I mentioned it whenever we were talking about these different sort of functions, like the positively asymptotic functions. It's like for theta, those things form an equivalence class, which is reflexive, transitive, symmetric, right? So, and then these in general are going to be greater than some n to the 1 over log of n, okay? And so there we have our complete little hierarchy list, and this encapsulates all of the identities that we were looking at there earlier. So that pretty much completes it for problem 3-3, which is what we were asked to do. We were asked to produce an arrangement, partition the list into equivalence classes. If and only if f of n is equal to theta of g of n, right? So, and that's what we've done. Let me think about this a bit more. Okay. Yeah, I think that's pretty thorough. There's more, like I keep saying about a lot of things, there's more that could be said about any of these given problems. It's just finite time, finite beings, that sort of thing. And so we'll close it off for now, and we'll pick up with the rest of the problems in the next video.